All right, guys. Sorry I unexpectedly had to be out today, but I'm going to pick up where we left off yesterday. So we started looking at writing the electron configurations with the periodic table. And like I said, this is a little bit harder to learn initially, but it tends to be easier in the long run. But if you like the diagonal way better, do the diagonal way. So our first example we're going to do is titanium. And titanium is number 22 on the periodic table. So titanium, when we're looking at the periodic table, is going to be right here in that transition metal in the D block. So like we said, with the blocks, that tells us how the configuration is going to end. In order to write the configuration, we're literally going to go row by row on the periodic table until we run out of electrons, until we hit our target element. So like we're going to start on the first row, and the first row goes through hydrogen, helium. That is our S block. So that's row 1, block S, and that was 2 elements wide with hydrogen, helium. So that's the 1s2. And that's the end of our first row on the periodic table. So then we go to the second row. The second row goes through the S block, which is 2 elements wide. So that's 2s2. Continue on our second row. It goes straight across to where boron is. Go through our second row, P block, so 2p. And if you count, that is 6 elements across. So it's 2p6. That gets us to the end of the second row. So we're going to continue working on our third row. So our third row, we go through our S block. So 3s, and that is 2 elements wide. So 3s2. Keep going across our third row. It goes straight across and then through our P block. So that's 3p. And that's 6 elements across, so it's 3p6. And then we get to our fourth row. This is the row that our target element is on. So we go through 4s, which is 2 wide. And then titanium is actually in the D block. So remember the D block, we said the principal energy level is the row -1. So since we're on the fourth row, subtract 1, this is going to be 3D. And if we count, titanium is the second element in that block. So it's 3D2. And you can always kind of check behind yourself. If you add up our superscripts, it should equal 22, our number of electrons that we started with. And we can do the same thing with neon. I'm going to switch colors to make it a little bit easier for you to see. So if we look at neon, neon is number 10 on the periodic table. So if you locate it, it is at the end of our second period on the periodic table. So we would treat this the exact same way. We would start on row 1. Row 1, we go through our S block, which is hydrogen, helium. So row 1, block S, and it was 2 elements wide. Then we go on to our second row. That goes through 2s, which is 2 elements wide. So 2s2. And then we get into our P block. Now this is where neon is. And if you count, neon is the 6th element in our P block. So it's 2p6. And one thing that you'll notice is we said that full or half full orbitals are most stable. Noble gases always have full orbitals. I'm going to come back to lead in a minute after we do abbreviated configurations because that one is so long. I want to show you what to do with this. So with our noble gas configurations or abbreviated configurations, because some of them are going to get so long. So like if we do lead, and I'll show you the long way and the short way with lead. So yet again, let me change color so you can see it a little bit easier. Let me not do red. Let's do this like purpley color. So lead is number 82 on the periodic table. So it's way down there. So if we look, it's actually way down here in our P block is where we're going. So to get to lead, we have to go through the first row of the periodic table. So row 1, block S, and that's 2 elements across. Then we have to go to the second row. Second row, S block is 2 elements across. Then we have to keep going on the second row, which goes through P. We go all the way through that second row. So that is 2P, and it's 6 elements wide. Then we go to our third row. So that's 3S, and that's 2 elements wide. Then we keep going across our third row. That's 3P, and it is 6 elements wide. Then we get to our fourth row. So we have 4S, which is 2 elements wide. Then it goes through 3D, which is 10 elements wide. Because remember that row number -1. Then we're back to P. So remember P, the principal energy level, is the row number. So then it goes to 4P, which is 6 across. Then go to the next row. So we have 5S, which has 2 elements. Then that goes into 4D because you subtract 1 from the row number, and that is 10 elements wide. Then it goes through 5P, which is 6 elements wide. And then we're on the 6th row, which is where lead is located. Don't forget that your inner transition metals, remember, go right here in your periodic table. So this top row of the periodic table, or of the inner transition metals, is actually part of the 6th row of the periodic table. So we have to go through 6S, which is 2 elements wide. Then comes our F block. So we have to go down here and go through our F block. Remember, our F block was the row number -2. So that will be 4F, and that is 14 wide. Then it comes back up and goes through our D block, which is the row -1, so that's 5D, 10. And then we're in our P block where lead is. We're on the 6th row, so it is 6P. And lead is the second element in that row, so it's 6P2. Whenever you're using the periodic table and using that F block, it does get tricky because our periodic table actually has the first element of the F block printed in the D block. So it does get a little confusing, but we tend to not use those super large elements. But those are ones that may need some additional support. So like I said, some of these can get really long whenever you get further down the periodic table. So there is a shortcut. Our shortcut is to do noble gas configurations or abbreviated configurations. This allows us to start with the noble gas before the element that we're writing a configuration for. And by writing the symbol of that noble gas, it takes away all of that beginning stuff that's very repetitive. And then we only have to write the configuration for the specific row that that element is on in the periodic table. So for example, cobalt. And I'm just going to draw my little periodic table so I can kind of show you what I'm talking about since I'm not standing in front of you. But cobalt, if you look for it on the periodic table, is number 27. It's right here in our transition metals. Now, that's not a huge element, so that can be a little bit trickier, but it's still going to take us some time to write, so we can still abbreviate it. So to abbreviate cobalt, you literally want to put your finger on cobalt, go up and all the way over to the right, one row, so up one row and all the way to the right, to figure out what noble gas is directly before cobalt, which will lead us to argon, is the one that's over there. So to signify that argon's the noble gas before cobalt, we write the symbol of argon in brackets. That accounts for 18 of our 27 electrons, just by having that symbol there. So we can subtract 18 from our overall count, and that means that we only have 9 electrons that we have to place. Where it gets tricky is figuring out where to start. So I kind of want you to put your finger back on cobalt, and if you look, cobalt is on row 4 of the periodic table. That means that we are going to start at 4s. Whether you use the periodic table way or the diagonal way. Since it's on row 4, we're going to start at 4s. So we start at 4s. That can hold 2 electrons. That's 2 elements across. Now we have 7 left that need a place to go. So after 4s is 3d. And we can put those 7 electrons in there. And then we are out of electrons, so we're finished. So that did save us some time writing that out. I'm going to change uranium to lead so you can see what this looks like in terms of our last example. So lead is Pb. Remember, that was 82 electrons. And it's down here in our P block. So the noble gas before lead, if you put your finger on it, go up one row and all the way to the right, is xenon, which is Xe. So we can write Xe in brackets. Ooh, sorry, my screen went crazy. And that accounts for 54 of our 82 electrons. So that's going to take out all that beginning stuff that's repetitive. So when we subtract, we're now going to have 28 electrons left that we need to place somewhere after noble gas. So then if we look, lead is on row 6 of the periodic table. So that means we're going to start with 6s. So 6s, and that's 2 elements across, or it can hold 2 electrons. Now we have 26 left. Remember, our F block is inserted there, so it goes from 6F, or 6s to 4F, and that's 14 elements across, or it can hold 14 electrons. Now we have 12 left. After 4F, we're in our D block, so that's 5D. And that can hold 10 electrons, so we have 2 left. And then after 5D, we're back in our P block, so it's 6P, and lead is the second element. So that took out a lot of that beginning stuff, but it's still the same configuration. It still has the same ending on it, which is what we're looking for. One that's a little bit bigger is radium. Radium, if you're looking for it, is number 88 on the periodic table, which is down here in the bottom left corner on row 7 of the periodic table. So if we wanted to figure out how to write radium, If we go up one row and all the way to the right, the noble gas before radium is radon, which is Rn. So we would simply have the symbol for Rn. And that accounts for 86 of our 88 electrons. Then we only have 2 electrons left that we need to place. Since radium is on the 7th row of the periodic table, we're going to start at 7s. And that is 2 elements across, or it can hold 2 electrons. And then we're out of electrons. So that is much shorter than writing out a full configuration. All right, another thing that we may come across is ions and writing their electron configuration. This is something that you're going to see in our flame lab as well. So remember we talked about last unit, ions are substances where an atom has an unequal number of protons and electrons. So it either gains electrons or loses electrons and has a charge. So remember, the charge is equal to the number of protons minus the number of electrons. If there's a positive charge, it means that the ion lost electrons, therefore there's more protons. If we have a negative charge, that means that the atom gained electrons and there's more electrons than protons. To do a configuration of ion, you're going to do the exact same pattern, the exact same steps, but you add or subtract the charge, however many electrons were lost or gained, from the total number of electrons. And it's always the opposite. So if you have something that is a -2 charge, what that means is you need to add 2 electrons to your total number. It's always the opposite of the sign. If you have something that's a +1 charge, that means that you subtract 1 electron from your total number that you have. So you're going to go through the exact same steps as every other electron configuration, but your beginning number of electrons changes. So let's look at these. So up here I have magnesium, which I tell you has a +2 charge. We're going to go over at a later time how you know what charge they are. But magnesium on our periodic table is number 12. And since it tells me that it's a +2 charge, that means that it lost 2 electrons. So I need to subtract 2 electrons. So I actually only have 10 electrons there that need a place to go. So filling in my 10 electrons, or going to number 10 on our periodic table, it's going to go through 1s2 to go down to 8, 2s2 gets us down to 6, and then we have 2p, which can hold 6. So it simply took away those outer level electrons, those valence electrons. Let's look at oxygen. Oxygen, it tells you, has a -2 charge. So oxygen originally has 8 electrons. If there's a -2, that means we need to add 2 electrons, which is going to be a total of 10 electrons. So the configuration for the oxygen ion is going to be the exact same. The 1s2, 2s2, 2p6. So when we have ions, they end up having the same configuration, because what happens is it matches the configuration of the noble gas, because that's what's stable. So remember we talked about stability yesterday. I don't know why I couldn't either. So if we look, neon number 10 has 10 electrons. Its configuration is 1s2, 2s2, 2p6. So anytime something forms an ion, it ends up with the same electron configuration as a noble gas. Let's do chlorine just for good measure. Chlorine is number 17 on the periodic table. Since there's a -1 charge, that means we add 1. So that's 18 electrons, which is the same number of electrons as the noble gas closest to it, argon. And if we write out our electron configuration, it's 1s2, 2s2, 2p6, 3s2, 3p6. And whenever you have things like magnesium, neon, and oxygen that have the same electron configuration, we refer to these as isoelectronic. So remember, isotope were the same element. Isoelectronic means they have the same number of electrons. We're not going to deal with that too much at this level of chem, but that can come up in like AP and other classes you may go to. All right, last thing we're going to look at dealing with electron configurations is the orbital diagram. This is another way of showing configurations, but it's more of a visual representation. Whenever we're drawing orbital diagrams, there are 3 main rules that we kind of have to keep in mind. First one is our Aufbau principle. This says the electrons enter the orbitals of the lowest energy first. This is the same thing we've been doing with electron configurations. This is our diagonal order, is the Aufbau principle. So that means that we fill 1s, then 2s, then 2p, things like that. And orbitals of a sublevel are of equal energy. So like the s sublevel has the lowest energy, but it only has 1 orbital. But remember, our p sublevel, we said has 3 orbitals. Well, those 3 orbitals are all going to have equal energy. One of them is not going to be stronger than the others. So it doesn't matter which one of those orbitals we put electrons in or fill first. That doesn't matter because they're all the same energy. Our second rule is our Pauli exclusion principle. This says an atomic orbital can describe at most 2 electrons. So that was our rule where we cannot have more than 2 electrons per orbital. That's what gave us those maximum numbers that each sublevel could hold. So 1 or 2 electrons can occupy an orbital, but they must have opposite spins of clockwise or counterclockwise. So if there are 2 electrons in the same orbital, they have to have opposite spins. And the way that we represent the spins are by arrows. So we will show the arrows pointing in different directions to show that the electrons have different spins. So like one will spin up and the other will spin down. And our third rule we look at, this we haven't talked about in any way, shape, or form, is Hund's rule. So this says for orbitals of equal energy, like my p orbitals that I have up top, we said those are all equal energy. 1 electron is going to enter each orbital until all orbitals contain an electron before pairing. So what that means is if we have 2 electrons to go in this p orbital, we have to separate them because you have to put 1 in each orbital before going back and pairing. You would not have them paired up because it's not stable. Stable configurations are going to have half full or completely full orbitals. And we're going to do a couple examples, but this is just a visual representation of those electron configurations. So we're still going to be filling the same order, the same number of electrons. We're just drawing them in lines or boxes and showing the electrons as arrows instead of as superscripts. So let's do a couple examples. So let's do sulfur. Sulfur is number 16 on our periodic table. So we have 16 that we have to go through. So our first orbital or sublevel we go through always is 1s. We said s sublevels have one orbital, so it has one line, one place for electrons to go. And like I said, sometimes you'll see these as lines or boxes. I think boxes tend to get a little too cluttered, so I personally do the lines. We're going to put our 2 electrons in this 1s orbital, but remember, when 2 are in the same orbital, they have to have opposite spins. And you can do the single-sided arrow to save time, is fine. So now we're down to 14 electrons. After 1s comes 2s. And we said s only has one orbital. And that holds 2 electrons. So yet again, they have opposite spins. Now we're down to 12 electrons total. After 2s comes 2p. And our p orbital has, or p sublevel has 3 orbitals. So there's 3 lines representing our 3 orbitals. And then we have to fill them in. So we put 1 electron in each before going back and pairing. And we had enough to fill that, so now we have 6 electrons left because there are 10 drawn already. After 2p comes 3s. And s we said has 1 orbital, so that can hold 2 electrons. So now I have 4 electrons left. Now I come to 3p. And p we said has 3 orbitals. And we only have 4 electrons. Remember, we have to put 1 in each before going back and pairing. And it doesn't matter which one you put that second one in, as long as you should have 2 unpaired electrons right now. A question it could ask is, it could ask you how many unpaired electrons there are. So like here, there are 2 unpaired electrons. That will deal with whenever we get to bonding. If it asks you specifically the valence electrons are the outermost electrons. So like our level 3 is our outermost energy level. So that would have a total of 6 valence electrons when we add all those together. Alright, let's look at titanium. I'm going to change colors so you can see it a little bit easier. So titanium is a little bit bigger. We have already written the electron configuration for titanium, but let's do it using the orbital diagram. So titanium is number 22. So you can locate that on the periodic table. It is in our D block. So we are going to have to go through to a D block. So our first level that we fill always is 1s. We said that has 1 orbital. We can go ahead and fill that with 2 electrons. So now we have 20 left. After 1s, it goes through 2s, which has 1 orbital and can hold 2 electrons. So that's 18 electrons left. After 2s comes 2p. Remember, p we said has 3 orbitals and can hold a total of 6 electrons. So now we have 12 electrons left. After 2p comes 3s. That has 1 orbital and it can hold 2 electrons. So now we have 10 left. After 3s comes 3p. And we said that has 3 orbitals and can hold 6 electrons. So now we've drawn 18 electrons and we have 4 left. After 3p comes 4s. And that has 1 orbital and can hold 2 electrons. Then I have 2 electrons left. Now we're in our D block. We haven't drawn a D block yet. But remember, D block can hold up to 10 electrons, which is 5 orbitals. So 3D has 1, 2, 3, 4, 5 orbitals. and we have 2 electrons left. So remember, we have to put 1 in each before pairing. So these 2 electrons are not going to be paired, but it does not matter which 2 lines you put them in. I just always happen to go from left to right, but they could be in the last 2 as long as they are not paired together. This one, the trick with valence electrons. Remember I said valence electrons are in the outermost energy level. Well, if we're looking at titanium, the energy level that has the highest principal energy level is 4. So only our 4s electrons are valence electrons. So this only has 2 valence electrons because there are only 2 electrons in the 4th energy level. Even though we placed electrons after that, they do not count as being in that higher level. They drop down to the previous level. That can be a little bit tricky with these overall. Right. That is where we're stopping today. You are able to, on that first page of your homework on the back right side, you're able to complete all of the electron configuration stuff on that back right side. And on the top of the second page, there's a section with orbital diagrams. You are able to complete those. Also in Canvas, we have one of our mazes, the electron configuration maze. And we did one of these in our first unit, I believe, where, remember, we have the maze and you can draw the arrows to work your way through the maze, matching up the element with its electron configuration, or the rule with its definition. That will be due on test day, just like everything else. For first period, because I had to unexpectedly be out today, and I had a previous appointment tomorrow, our quiz on Thursday will be a practice quiz. So you can take it to see what you would have scored, check your work, but it will not count against you since I'm not here the 2 days leading up to it. Your test on Friday is still going to be on Friday and will still count for credit. So please pay attention to that and make sure that you're practicing. As always, the answer key will be provided for you to check your work, and let me know if you need anything.